Welcome back to week one of vibrations. This is video 2. I'm continuing on. We want to talk about vibration types. All right, I'll just jump here. Vibration types. These are important things, and we can also think some of the breakdown of the early part of the course is going to be related to how these run. We started with something called free undamped. That is really just your typical spring and mass, right? So we have a K and an M. I should try to be a little bit neater here. Let me try to be neater. See, I'll rest my hand. And it's not that much better. Resting the side of my hand on the little touchpad. There we have M and K. So this thing its results will go back and forth and back and forth and back and forth. And as I alluded to in the last class, it'll make a sine wave, right? So if you just are paying attention to this parameter, let's call it y, and here's y, and here's time. If you just cite this thing through time, it will act this way or here. We could also have a forced undamped, which is doing the same thing right here. I want to try to make it neater. I gotta go for neatness here too. Don't be lazy. All right, so you have the M and the K, right? And this thing, by the way, this generated an MX double dot plus KX equals 0. Well, the forced one is now going to have a force applied to it, and that force might change with time. Well, it probably will. All right. And quite often we'll go ahead and make that force also a sine or a cosine wave applied onto the thing. So you'll have an equation that's like, I don't put the dots on top of the M. X double dot plus K X, and that equals Ft, right? A lot of times we'll put the forcing function on the right-hand side. We're kind of ignoring the signs of these right now. And I'm not going to try to graph this because we don't quite know what that will look like right in there. But a lot of times, if this happens to coincide with the natural frequency, which I brought up a couple times, we're just about to explain what it is, that will cause the thing to have a large, unreasonable motion. All right, so now we have, so that's one category. We have the free undamped and the forced undamped, right? Now we have the free damped, where it's the same thing as up above, but we'll make the mass wider, and we'll put sometimes called a dash pot. We could think of it as a hydraulic cylinder or shock absorber type of thing. And what we'll find is we'll have some initial motion, but it will damp out with time, right? So up here, it kept on going forever. Here, it'll actually damp, and we will see that we could actually find there's a kind of a pattern to this right here. So that's what we want to consider. And then lastly, we will take a look at the same thing, but with a force applied to it, right? And so we'll have an Ft. Oh, and by the way, I meant to write this. We'll have mx double dot plus c times x dot plus k times x equals 0. Right, so that's going to be the equation of motion for the free damped thing. We will probably usually set it up actually for a particular set of circumstances, but for this very basic of scenario, that's what we have. And then, by the way, there's a C next to that to mark up there. The same thing here, C and K and M. And I really, with the force one, it depends on what kind of pattern of the force, what kind of sine or cosine or something else that's time dependent of the force that's taking place. Here's the equation of motion for that, just to finish up, right? So there's the force as a function of time that will happen. A lot of times what we'll do instead of drawing the time history of the forced systems, whether it be forced damped or forced undamped. We'll have a graph that we take a look at, and we'll see if this has an omega F or something like that. This will be a omega F versus omega N, which is the natural frequency of the system. And I'm not going to draw out the curves, but we'll see when it equals 1, then it goes way up into high space, because you shouldn't do that. All right, so moving on. This is the introduction to give you the idea of the vibration types and the organization of the class, so it's worth recognizing that. Okay, so here is a big important thing, and oh, by the way, no, I'll wait for later. So what is natural frequency? And my answer is the note of a thing. So if you were to take a wine glass and you were to hit it with your finger and you hear a bing, you could get a tuner and you could find out that's the natural frequency. Right now, there's a bunch of frequencies happening at the same time, but there's a dominant one. There's a main one, and that's the principal natural frequency. I think you got the right word. And so if you tap on a thing, it's related to resonance, right? So here's one of the reasons why we care about it. If you were able to sing the exact same note with a really powerful voice, you'd be able to break that glass, right? Or at least that's what we've been told for years and years. I can't remember. Maybe I need to look it up on what's the name of that show, Lori, that you look stuff up on, where they Mythbusters. That's the one I was looking for. Anyway. So a natural frequency. So when we're having what is natural frequency, let's also take a look at the two main equations, or the very main equation here that we want to care about. So here's omega. It's not W. Subscript little n for natural is the square root of K over M. And this is often referred to as circular frequency, circular natural frequency, because it is in radians per second. We often don't want to deal with that, so we instead have the natural frequency here that we will deal with when we want some real numbers. We'll divide that by 2 pi. So we're dividing it by 2 pi for every rotation of the thing, and then this comes out into hertz, which is, of course, 1 over time, 1 over seconds. So here's the actual natural frequency, and here's the circular one. Nat freak. But here's the one when we just say frequency, we kind of use the word interchangeably a lot of times, but we got to remember when we're finding this as this simple equation right here, this is for the simple spring mass. It's not always equal to this, but for a spring mass system, it's equal to this. And in other situations, it's got a form that kind of is similar to this. So we want to think of natural frequency as the square root of stiffness over mass. And if you want to get the actual number that you want to use and report, you do it in hertz. And why do we care about natural frequencies? Well, a lot of it is the same thing we mentioned in the first video. We worry about resonance, really saying. It's really resonance. And resonance is when you match the natural frequency with a source, with an oscillating source. Oscillating. I think that's right. Source. I'll just put the source right there. So you can excite something, and we'll use that isolating, the excitation, as we like to say, excitation. So an excitation source onto the thing. And then maybe we worry about it because of this is also called sympathetic resonance. Sympathetic resonance. Sympathetic resonance means that, like, um, I'll demonstrate this in class. If you have two things of the same frequency next to each other, I can actually get the other part to start vibrating simply because there's some type of either physical contact or they're contacting the same part. We could actually get the thing to start ringing. And we could do that with tuning forks. And I have two tuning forks of the same 440 hertz, or they're 110, I can't remember. And we'll demonstrate that in class. We have sympathetic resonance. And as I mentioned in the previous class, things can break because they're being excited at their natural frequency. They could break faster than they would otherwise. So let's move on to the next video. And that's the end of video 2.